You've gotten an x-ray before, right? Probably at the dentist, or maybe you've broken a bone before. But did you know that x-rays can be used to examine individual atoms? Not only that, you can use x-rays to track the progress of a chemical reaction or how atoms change positions within a material. It sounds like science fiction, but it's a real capability, a kind of atomic vision happening in labs around the globe. But how is this possible? How can we witness this intricate dance of atoms? The key to this science is a remarkable method that you've probably never heard of. This is the story of X-ray absorption spectroscopy. Hello and welcome to the Chemist's Codex. My name is Peter and I like to find stories in whatever catches my interest because I believe those stories can teach us more about ourselves. The last time I talked about x-rays, people seemed to really like it, so I'm continuing the story to talk about one of my favorite methods for looking at matter. If you haven't watched my previous video about X-ray crystallography, make sure to check it out, after you finish watching this video, of course. For centuries, the proverbial halls of science echoed with a rather important question. What are things really made of? We've known about atoms for a while now, but knowing the ingredients of a material is only the first step. The key to understanding a material lies in the architecture, how the atoms actually arrange themselves and connect with each other. It's the difference between graphite, a material soft enough to write with, and diamond, the hardest substance we know of. Both are just carbon atoms, but the arrangement of their atoms makes them drastically different. This can be the difference between a battery that dies after a year and one that lasts a decade. But how do we see this atomic dance that underpins our entire world? I've already talked about the discovery of X-rays in my previous X-ray focused video, so I'm going to give a short summary here just for context. In 1895, the physicist Wilhelm Röntgen was meticulously experimenting with a cathode ray tube, specifically a Crookes tube. He had the tube completely covered in black cardboard to block any visible light that might be emitted. As he worked, Röntgen noticed a screen coated with a fluorescent chemical sitting clear across the room, starting to give off a faint, ghostly green glow. After several rounds of tests and even showing his wife the bones in her hand, Röntgen accepted he had discovered a new type of light, calling them X-rays. As scientists frantically began to study these X-rays more closely, they found something intriguing. When you pass X-rays of different energies through a material, they aren't absorbed smoothly. At very specific energies unique to each element, the absorption of X-rays would suddenly and dramatically spike. These spikes were named absorption edges, and they were a sort of fingerprint, a clear identifying signature for each element in a sample. For a while, identifying elements with absorption edges was a useful trick, another useful tool in the field of spectroscopy. But a deeper, more subtle mystery remained. Just after these sharp, well-defined edges, scientists noticed faint, mysterious wiggles in their data. The absorption didn't just fall off smoothly back to the baseline. It oscillated, like fading ripples on a pond after a stone is tossed in. For decades, those wiggles were mostly ignored, a curious artifact, maybe a bit of noise in the data that nobody could properly explain. They were a quirk of the measurement, but they were also the first clue in a puzzle waiting to be solved. It was a kind of ghost in the machine, a cryptic message from the atomic world that we hadn't yet learned to read. To decipher this message, we would need to abandon the comfortable world of classical physics and take a radical leap in the counterintuitive world of quantum mechanics. The key to finally understanding those mysterious wiggles didn't come from studying X-rays themselves, but from understanding what happens when an X-ray photon collides with an atom. By the early 20th century, our picture of the atom was becoming more and more clear. We now understood it as a dense central nucleus surrounded by electrons existing in distinct energy levels, typically referred to as shells. To get a grip on X-ray absorption, you have to imagine an incoming X-ray as a tiny packet of energy rather than a wave. That's what a photon is. For an atom to absorb the photon, the energy has to be just right. The photon needs to have enough energy to do one thing, that being knock one of the atom's innermost, most tightly bound electrons completely out of its orbital, ejecting it from the atom entirely. That sharp spike of the absorption edge, then, represents the minimum energy required to free that core electron. But what happens to that newly freed electron? This is where it gets interesting and where quantum mechanics makes a big difference. This electron isn't just a tiny particle flying off in a straight line. It's also a wave. The ejected electron, now called a photoelectron, radiates outward from its parent atom as a spherical wave, spreading out in all directions. Think back to the metaphor of dropping a pebble into a pond. But that pond isn't empty. There are other pebbles being thrown in this case representing the neighboring atoms. The wave from the photoelectron travels outward, hitting these neighboring atoms and then scatters off them. Some of that wave is scattered back towards the original atom from which it came. So you have the original outgoing wave of the photoelectron, and you have all these backscattered waves arriving from the neighboring atoms. These waves interfere with each other, lining up to reinforce each other, creating a stronger wave in constructive interference, or canceling each other out in destructive interference. This interference pattern directly affects the atom's ability to absorb another X-ray. If the waves interfere constructively, it enhances the probability. So then naturally, destructive interference decreases the probability. As you increase the energy of incoming X-rays, the wavelength of the ejected photoelectron changes, which in turn shifts the entire interference pattern. So those mysterious wiggles that scientists had been seeing for some 50-odd years, they were a direct recording of this interference. It was a phenomenal realization. The wiggles weren't noise. They contained exquisitely detailed information about the local structure surrounding the absorbing atom. The distance to those neighbors, how many neighbors there were, even what kind of atoms they were. It was all encoded in the shape and frequency of those oscillations. The ghost in the machine was starting to speak, but the message wasn't clear. Scientists were going to need a much, much brighter light. In the early days, making X-rays was a pretty crude process. You would essentially take a metal filament, run an electrical current through it with enough power to get electrons to pop off, and fire them at whatever you wanted. The resulting X-ray beam was rather weak, unfocused, and spread out over a wide range of energies. Trying to measure the fine details of those wiggles with this type of source was like trying to read a newspaper by candlelight from across a football field. It required painstaking, days-long measurements that often yielded useless data. What scientists needed was a new source of X-rays, a light source that was incredibly bright, millions of times more intense than an X-ray tube. It had to be highly focused into a thin beam, and most importantly, the energy needed to be tunable. You need to be able to pick a precise energy, measure the absorption, then dial the energy up ever so slightly and measure again, mapping out those wiggles in excruciating detail. The answer came from the field of high-energy particle accelerators. Since the 1930s, physicists had been using large, circular machines to accelerate particles like electrons to nearly the speed of light for particle smashing experiments. They used magnets to bend the path of these electrons, forcing them to travel in circular paths. These scientists noticed a curious and somewhat annoying side effect. When you force an electron to curve while it's moving at near light speed, it emits a brilliant flash of radiation. This synchrotron radiation, as it was called, was a nuisance at first. It caused significant losses of energy within the beam of electrons, so more energy had to be pumped in to make up for it. But scientists eventually realized this wasted energy was exactly the tool the X-ray world had been searching for. Synchrotron radiation was millions, even billions of times brighter than the best X-ray tubes. It was naturally focused into a narrow cone of light, and with a little thing called a monochromator, which can select a single energy from the beam of light, scientists could select the exact wavelength of X-rays they wanted and tune it with incredible precision. Suddenly, building dedicated synchrotron light sources became a scientific priority. Inside these giant city block-sized buildings, electrons raced around a storage ring 24/7 guided by powerful magnets. These electrons travel at nearly the speed of light, and each time their path is bent by a magnet, they emit a blinding beam of X-rays. Scientists then build experimental stations called beamlines that tap into this light, funneling the powerful X-rays into heavily sealed rooms to run their experiments. With the birth of the synchrotron, the era of modern X-ray absorption spectroscopy had truly begun. The 1970s became the golden age for the technique, now formally known as X-ray absorbance fine structure, or XAFS. At these new synchrotron facilities, like the Stanford Synchrotron Radiation Light Source, a team of researchers, Dale Sayers, Edward Stern, and Farrell Lytle, finally put the pieces together. They had the theory of where the wiggles came from, and the powerful synchrotron light needed to accurately measure them. Their great breakthrough was in developing the mathematical framework to translate those wiggles from abstract data into physical reality. They developed what is now known as the XAFS equation, a powerful formula that connects the oscillations in the data to the local structure around the absorbing atom. This equation allows scientists to translate the world of those wiggles into atomic structure. The equation itself can look a bit daunting, but the idea behind it is beautiful. It treats the wiggles as a combination of different sine waves, all added together. But the real beauty of the equation comes from the relationship it creates between those waves, and physical properties like how long a bond is between two atoms and how many bonds an atom is making. Analyzing the data, then, is a kind of elegant reverse engineering. You take the wiggly part of the spectrum, a bit past the absorption edge, a region known as the Extended X-ray Absorption Fine Structure, or XAFS. I know, it's a bit confusing. Then you use the mathematical magic of a Fourier transform to convert this data from a function of energy into a function of distance. The result is a rather simple graph with a series of peaks, where each peak represents the most likely distance of the absorbing atom's nearest neighbors. It's like a one-dimensional map of the atom's local neighborhood. There's also a wealth of information in the region right at the absorption edge itself, a region called the X-ray absorption near edge structure, or XANES. This part of the spectrum is incredibly sensitive to the atom's electronic state, what chemists call the oxidation state. A subtle shift in the edge energy can tell you if an iron atom has a +2 or +3 charge, which can be crucial information for understanding a material. And the real beauty of this technique? It works on almost any kind of sample. Crystals, amorphous solids, powders, liquids, even gases. The question now was, what can we do with this? The impact was immediate and profound. A perfect example of the power XAFS holds is in batteries. In the case of a lithium-ion battery, the type of rechargeable battery used in phones and electric vehicles, the battery works by moving lithium ions back and forth between two electrodes. As it charges and discharges, the atomic structure of these electrodes changes, which is what causes them to degrade and eventually die. But you can't see that happening, which is where XAFS comes in. Scientists designed a special electrochemical cell that could shoot X-rays at, allowing them to put a working battery right in the beam and watch what was happening to the atoms inside as it was happening. Using XAFS, researchers could track the oxidation state of the cobalt or manganese in the cathode changing in real time as the battery charged. They could measure the bond lengths, watching them stretch and shrink as lithium ions moved in and out of the structure. This atomic insight has been critical for designing longer-lasting, safer, and more powerful batteries. The power of seeing the atomic world also has applications in the many industrial processes that rely on catalysts. Often, the crucial active site of a catalyst is just a handful of atoms, and their exact arrangement and electronic state determine everything. XAFS is the perfect tool for this because of its element specificity. Scientists can perform experiments watching how a catalyst structure changes in the presence of reactive gases, revealing the exact mechanism of the reaction step by step. This has led to more efficient catalysts for car exhausts that reduce pollution and save energy, and it's a key tool for developing the next generation of catalysts. In environmental science, XAFS help solve dangerous mysteries. When toxic elements like arsenic or lead contaminate soil and groundwater, the danger they pose depends entirely on their chemical form. XAFS can identify the exact chemical state of the pollutant and how it's bound to soil particles, helping scientists design effective remediation strategies to lock the contaminants away safely and protect ecosystems and human health. The list can go on and on. These are just a few examples of how XAFS is quietly shaping our world. From better batteries to future drugs, this technique has become an indispensable tool for discovery. From mysterious wiggles on a graph to a global network of massive machines that let us watch atoms in action, the story of X-ray absorption spectroscopy is a testament to scientific curiosity and persistence. It's the story of learning to read a language we never knew existed, written in the interference of electrons. Today, that journey continues. New generations of synchrotrons are being built that are hundreds of times brighter than their predecessors. And revolutionary free electron lasers can produce pulses so short they can capture the motion of atoms on a femtosecond timescale, the timescale of chemical bond formation. By learning to see the local world of atoms, we have gained the ability to engineer it. We can now move beyond trial and error and rationally design the materials of the future. Better batteries, more efficient solar cells, and ideal catalysts. We can do this all because we finally learned how to interpret some wiggles on a spectrum. Thanks for watching. XAFS was a technique I spent a fair amount of time with as a grad student, and it quickly became one of my favorites. The large range of applications and the flexibility on what types of samples you can use made it incredibly interesting to me. And I want to know if any of you have experience with XAFS, or maybe you've worked at a synchrotron before. Let me know down in the comments. And if you want more videos about the incredible science shaping our world, make sure to subscribe so you don't miss my next video.